Hi, everyone. I want to use this opportunity to run through homework number 8. Yeah, homework number 8, normal distributions, which is a pretty long homework, or at least it's got a lot of questions on it. A lot of them are pretty easy, though. So yeah, let's go ahead and get started. So let me pop over to here. Oh, this is the end of the assignment. Sorry, let me get back to the beginning. This was chapter 6. All right, so we're going to start with number 6. So there's a bunch of z-score questions I assigned here, and I like these a lot, personally. Well, I guess 6 isn't a z-score question, but anyway, yeah, so 6 and I forget the numbers. Let's let me have a quick look here. 6 and what's the next one? 6 and 7. All right, so we got 6, 7, and 8. So 6 is just, this is just a, do you recognize the notation, right? So this is a normal distribution with a mean of 3 and a standard deviation of 5. So sigma is 5. Mean here is -2, so mu is -2. So that's just notation. Do you remember the notation questions? Z-scores measure how many standard deviations above or below the mean a particular data value is. So if you have data values and you've got the distribution of the data values, then any one particular one can be compared to other things that it is like. And that's what z-scores are really for, is measuring things against their own distribution. So it allows you to measure things that are unlike by measuring them both versus their own distributions. So for instance, the one that I did in the homework, or excuse me, in the notes, was I had a whale and a human, right? A blue whale and a human. And so we had a blue whale that weighed a certain amount and a human that weighed a certain amount, and like who was more unusual. So that's what z-scores are for. We're going to use this, so I want you to keep this in mind when we're doing the next couple of questions, because they're really helpful. So we have 11, 12, 15, and 19. All right, so 11. What is the z-score of x equals 12 if it is 2 standard deviations to the right of the mean? It turns out this is just a trick question, basically. This x equals 12, which seems like the important part, is not. This is the important part. It is 2 standard deviations to the right of the mean. So z-score is 2. That's it. That's all you got to do there. Was number 12 the next one? Yeah, 12. So the z-score of x equals 9, if it is 1.5 standard deviations to the left of the mean, it's negative 1.5, because it's 1.5 standard deviations to the left. That's literally all z-scores measure. Number 15, suppose x is approximately normal with a mean of 2 and a standard deviation of 6. What value of x has a z-score of 3? Well, z-score of 3 means 3 standard deviations above the mean. 1 standard deviation is 6, so 3 standard deviations is 18, and 18 units above the mean of 2 is 20. So x is 20. That's the value. Then we have 19 and 23. Yeah, 19 and 23. So 19. Suppose x is approximately normal with a mean of 4 and a standard deviation of 2. What value of x is 1.5 standard deviations to the left of the mean? Well, okay, so 1.5 standard deviations to the left. So a standard deviation is 2. Remember that standard deviation is just a length, right? So a standard deviation is 2. So 1.5 of those is 3, right? 1.5 times 2 is 3. And we're going to the left, so it's negative. So we're going to go -3 from 4, which is 1. So x value is 1. And the last problem in this section is 23. X is approximately normal with a mean of 12 and a standard deviation of 6. What is the z-score of x equals 2? Well, you can see the calculation. Well, I guess I might as well use the formula here, right? So the way you want to think of this is 2 is 10 units below the mean of 12. And 1 standard deviation is 6, so we are 10 over 6 standard deviations below the mean. So let's we can also use a formula for that if that was not helpful. So here, let's let me draw a picture first, and then I'll just use the formula. So we've got, there we go. So here's 12. This is 2. And a standard deviation is 6, where we have n 12, 6. So a standard deviation is 6 units. So like that. So sigma equals 6, which is about, let's say, yay long. Right, so that's essentially what a standard deviation is measuring, is distance from the mean, or z-score is measuring how many standard deviations we are from the mean. So this is 6, and then we have a little bit more past that, right? So like 6 goes this far, and then we got a little bit more, but not quite 2 whole standard deviations, which would be 12 and all the way down to 0. So 1 sigma equals 6. So 10 units equals 10 over 6 sigmas. That was not the greatest handwriting there at the end. Let's clean that up just a little bit. Sorry, that was a little too messy even for me. Right, because a single sigma is 6 units. So 10 units is 10 over 6 sigmas, which is 1 2/3, right? So 5/3. So that equals 5/3, which is about equal to 1.67 sigmas. So that means that we are 1.67. Z-score is negative 1.67. And so therefore, Z equals negative 1.67. Now, you don't have to think this all the way through every single time. I actually prefer to personally. It seems a little bit easier and more intuitive to me, but you can certainly do this. You can also just use the formula. Z equals, so if you remember, it's x minus mu over sigma, right? So that's your formula for z-score. So this is 2 minus 12. Oop, that's supposed to be a 12. 12 over 6, which is negative 10 over 6, which of course, if you jam it in your calculator, negative 1.67. Right, so feel free to just use the formula if you like. I like to think it through, but I am partial to a lot of thinking and not a lot of formula usage. So whichever way you like it, it really makes no difference. I don't want to say makes no difference. Do whichever one you prefer. Most people will prefer one or the other. All right, back to the questions. This is my answers that I'm going to post. So the next question is 60 and then 61. So this is what I meant to click on. Let's go back here. 60 and 61. There we go. Okay. All right. So standard normal. So normal distributions here. So the patient recovery time from a particular surgical procedure is normally distributed with a mean of 5.3 days and a standard deviation of 2.1 days. So n 5.3, 2.1. What is the median recovery time? Well, normal distributions are symmetrical. And so the median is equal to the mean. That's true for every symmetric distribution, especially, well, not especially, which includes normal distributions, right? So the median is 5.3 right there. What's the z-score for a patient who takes 10 days to recover? All right, so we're going to do the same thing. Now, we kind of have to use the formula here, right? We get an approximate answer without using it, but it's going to be way better to use the formula, right? We've got decimal places here. It's not going to come out nice. So I'm just going to go to whiteboard, 10 days, and means 5.3, 2.1. Okay. So we got, for this problem, whoop, there we go. For this problem, we've got z is 10 minus 5.3 over 2.1, which is 4.7 over 2.1, which turns out to be something I forgot off the top of my head, 2.24 or something like that. Let's see what my answer said when I figured it out earlier. That is, just can't click on the right thing apparently. This one, yeah, 2.24. There we go. All right, 67. There we go. 2005, a bunch of students took the SAT. The distribution of scores in the math section was normal with a mean of 520 and a standard deviation of 115, which is kind of interesting. So I don't know if I've told you this before, but my job before becoming a math teacher was that I taught people how to take standardized tests, including the SAT and the ACT and a bunch of other ones. And the people who put on the SAT with the College Board, tries to make the average 500 and the mean 100. So what that means is that basically students who are studying a lot for it, and that you get a lot of perfect scores. There's a lot of people with perfect scores. So the distribution ends up being not quite normal at the edges. And I think that's messing with their scoring system here. Too many people are too good, basically. They study up like crazy and just get a perfect score. Anyway, that's a bit of a tangent. So we've got mu equals 520, sigma equals 115. Calculate the z-score for SAT score of 720. All right, we'll interpret that using a complete sentence, sure. So if we go here, we got it's 2.24, 1.24. We have z is 720 minus 520 over 115, which is 200 over 115, which is, I don't remember, some number. It's like 1.7 something, I think. 1.74, yeah, right here. So 1.74 is the z-score, 1.74. And so the way we want to interpret that is that somebody who scores 720 on the SAT math is 1.74 standard deviations better than an average student. That's it. That's the only interpretation I know for that. Part B. That's not the right thing to click on. There it is. That's the one I want. Part B. For what math SAT score is 1.5 What math SAT score is 1.5 standard deviations above the mean? What can you say about this SAT score? I'm not totally sure what you can say about the SAT score. We'll see it in a second. But if one standard deviation is 115, we just do 115 times 1.5, add that to 520, right? So we just go here. We just do 115 times 1.5. That's how far a z-score of 1.5 will take you. And then we have to add that to the mean because that's how far it is above the mean. And so we get 692.5. So the first thing I can say about this SAT score is that this is not an SAT score because SAT scores are only multiples of 10. So this is not an actual SAT score, and there are no legitimate scores that are exactly 1.5 standard deviations above the mean. That said, I would just say that this a person who scores, let's say 690. A person who scores 690 is 1.5 standard deviations better than the average student. I guess that'd probably be my interpretation of it. That one. Let's see. What did I just do? I did something. I'm not sure what it was. Apparently I clicked on a link, I guess. Sorry about that. All right, here we go. Oh, I probably clicked on this and it took me to 6.2. Yeah, okay. So in 2012, the math test had a mean of 514 and a standard deviation of 117. The ACT is an alternative to the SAT and is approximately normally distributed with a mean of 21 and a standard deviation of 5.3. That's interesting that their standard deviation got smaller. The ACT attempts to have their standard deviation be 6 and have a mean of 18, I believe. So they're sort of having the same problems as the College Board. I don't remember what's on the ACT, some other company. So mean is 21, standard deviation is 5.3. So one person took the SAT and got a 700, and a second person took the ACT, got a 30. So who did better is the question there. Now this is what z-scores are for, right? These are two similar things that are scaled differently, right? They're both like how well you did on a standardized math test, but then like you can't just compare a 700 and a 30 and a 700 on the SAT and a 30 on the ACT and expect to get some sort of meaningful comparison. You have to essentially put them on the same scale, which is what z-scores are for, right? That's literally the point of them. So I'm gonna make a new one. So z sub SAT is well, they get 700 with a mean of 514, I think, and a standard deviation of 117. And z sub ACT was we scored 30 with a mean of 21 and a standard deviation of 5.3, right? And so you can jam these both into your calculator. It turns out that the ACT is a little bit better. This is like 1.6 something. This is 1.7 something. So that means that the person who scored a 30 on the ACT, which is a very good score, did a little bit better than the person who scored a 700 on the SAT. Although both students did quite well and will probably have no trouble with their college admissions, at least if they're based on this. Yeah, so you just calculate them that way. Just use the formulas here, and whichever one's bigger, that's the person who did better. In this case, was the ACT paper. All right, I forgot what the next question was. 68. 68, 69, yeah. Okay, so patient recovery time from a particular surgical procedure. Did we do this one before? I feel like we used this setup before. Has a mean of 5.3 days and a standard deviation of 2.1 days. Probability of spending more than 2 days in recovery. So what we want to do here is I'm going to draw a graph. Like we're going to draw graphs for basically all of these. Yeah, so let's just go sketch a graph. You want to get in the habit of drawing graphs for these things. By the way, it's really, really helpful, especially when you're starting out. Once you get a lot better at it, it kind of becomes unnecessary. But especially at the beginning, this is so much easier. So much easier. 5.3, 2.1. Now, one thing that people often mess up is they look to put the standard deviation on here somewhere. It does not go there. This is the mean. The standard deviation does not appear as a number on here anywhere. It's a distance from the mean, right? So, but that doesn't mean like if I go one standard deviation from the mean over here, this is not 2.1. It's that this distance right here would be 2.1. So you could, if you wanted to, you could do like this could be 3.2, 3.2. This could be 1.1, right? So I could keep going down, counting by standard deviations. And in fact, I know some people really like to do that. I don't bother. This is just a visual aid as far as I'm concerned. I don't care about getting the standard deviation on there. I do always write it. I do always write it down up here because we need to know it, right? We're going to need to know it in order to do the problem. But I don't want to get it anywhere on the distribution. Sorry about that. Okay. I forgot what I was saying. 5.3, 2.1, and then we had some question about that. Oh yeah, what's the probability of spending more than 2 days in recovery? So quite high, right? The average is 5.3 days, so we're not expecting to. We're expecting it to be quite a lot. So 2 is like over here somewhere. I don't care if that's to scale. I just want to get it. On the distribution as a visual aid. And then probability of spending more than 2 days is that area. Because remember, that probability equals. So to answer this, you want to do normal CDF. So normal CDF of 2 up to infinity, right? Because there's no technical upper limit for number of days you could spend in recovery, with a mean of 5.3 and a standard deviation of 2.1. So let's go look at that. So that is second bar. So distributions, we're going to use normal CDF. Lower bound is 2, upper bound is some large number that we'll substitute for infinity. Mean was 5.3 and the standard deviation was 2.1. And yeah, I know this is only 100,000. That's way, way, way bigger than 2. And the thing you really want to notice is that the distance between these two things is much, much larger than this, right? So I wouldn't necessarily want to use like 10. Right, that's not far enough, but even 100 would probably be plenty. So I'll just do a bunch of those, and I'll come back and do this with 100 and see what it looks like. So we had 94.2%, something like that. So if I came back and did that with just 100 instead of whatever 100 million I used, let's see what happens. Right, so notice it's the same to 10 decimal places. It's 10, right? Yeah. It's the same to 10 decimal places, so you don't have to go nearly as crazy as I am with the zeros to get something that's basically infinity as far as this calculation is concerned. So 94.2% is what we're looking at here. I think that's one of the answers. Yeah, it's D. Right, it's this guy right here. So the answer is D. the 90th percentile for recovery times. So 90th percentile. So now we've got, so the same distribution. All right, so it's still the same distribution. I'm gonna draw it again anyway. Just to have a fresh one to write on. It's still the same distribution, but they're asking for the 90th percentile. That means the number that has that has 90% of the area to the left of it and 10% to the right. I didn't draw that all that well, but I hope you understand what that means. And so the thing we're looking for is not a number of recovery days, or excuse me, the thing we're looking for is a number of recovery days, not a probability like we were looking for here. So it's a data value. So when we are looking for a data value, but we have a probability or an area, that's when we want to use inverse norm. So let's go do that. So I'm going to do inverse norm of 0.9 with a mean of 5.3, standard deviation of 2.1. See what we get. Inverse number 3. Area is 0.9, mean is 5.3, standard deviation is 2.1. Now, I don't know if you're using the VMware version, of course, you do have left, center, and right. And this is asking you where is that area? Is it the area to the left of the number you're looking for, or the area to the right of the number you're looking for? Or is it like the middle 90%, which has 5% on either side? Now, if you have a physical calculator that you're using, you almost certainly don't have this tail option. I wish they just didn't have this, to be honest. But not having it means that it's just left on. It's on left all the time. So when I'm doing these, I'm just going to do it on left all the time. For one, because I'm used to it, and for two, because that's what a lot of people who have physical calculators are going to be stuck with. 7.99, which is one of the answers. Let's see. There we go. So this is a number of days. So 7.99 days. All right. What's the next one? 75. Okay. Computer, did I pick the wrong one? Probably did. 75. Percent of fat calories that a person in America consumes each day is normally distributed with the mean of about 36. So it means 36% of the calories we consume are from fat, and a standard deviation of 10. So 10%. Suppose that one individual is randomly chosen to let X equal percent of fat calories. So X is, so here they're just looking for the name of the distribution. So this is, the thing that goes here is an N for normal. This is the mean, which is 36, and this is the standard deviation, which is 10. Find the probability that the percent of fat calories a person consumes is more than 40. So here I want to find the probability that little x is greater than 40. So I want, let's do a graph. So I should have just done this first, right? As soon as we started doing a problem with normal distribution in it, this is N 36, 10. 10 doesn't go on there anywhere, but 36 goes right in the middle here. And their question was, what's the probability that we're greater than 40? So 40 is over here, and greater than is that way. So I want to do normal CDF of 40 up to infinity with a mean of 36 and a standard deviation of 10. That's what I'm going to do. I'm just going to jump over the calculator and do it. So we've got normal CDF, 40 up to infinity, with a mean of 36 and a standard deviation of 10, 34.46%. There you go. Graph the situation, shade in the area. We did that. Great. Find the maximum number for the lower quarter of percent of fat calories. Boy, that is awkward. Awkwardly phrased. Sketch the graph and write the probability statement. I'm not totally sure what probability statement they mean. I think I might know, but let's do this. So the lower quarter. So that means that we're looking for whatever this number is, question mark here, that gives us an area of 25% down there, right? So for this one, to find that, I want to do inverse norm. I want to do, IMV norm of 0.25. So I think what they're saying is that the probability that X is less than question mark here equals 0.25. I believe that's the probability statement that they're looking for. So whatever question mark is, we know that the probability that x is smaller than that is 25%. So let's go find that. It's an inverse norm of 25% with a mean and standard deviation of these guys. So we got inverse norm, that is here, so number 3. Area is 0.25, mean is 36, standard deviation is 10, and again, we're just using left. 29.26, something like that, 29.26% is the top end of the bottom quarter. Yeah, so this would be 29.26, and then this guy is 29.26. Right, that's what goes there. And I think that's what they were looking for. I didn't go look it up in the book. I probably should have, but I didn't. Yeah. All right. What was the next question? 80. This is the last one from chapter 6, or rather 80 is. Oh, sorry, I never switched away. 80. Terry Vogel, an amateur motorcycle racer, and given the fact they use a first and last name, this has to be one of the author's friends. Averages 129.71 seconds per 2.5 mile lap in a 7-lap race with a standard deviation. That's a very small sample. Maybe she's had a lot of laps with a standard deviation of 2.28 seconds. The distribution of her race times is normally distributed. We are interested in one of her randomly selected laps. Okay. So in words, define what the random variable x is. It's whatever they said we're interested in. One of her randomly selected laps. So random capital X here is the distribution of all of her laps. One at a time. X is approximately normal, so that's an n with a mean of 129.71 and a standard deviation of 2.28. Percent of her laps that are completed in less than 130 seconds. So let's go draw a graph. So we have n 129.71 comma 2.28. I think I remembered. I think I got that right. 129.71. So what is the percentage that are completed in less than 130 seconds? So that's right here, right? So 130. And we're looking for less than, so that's this area here. So notice that lower is better here, right? Lower is faster. Less time equals faster speeds. Yeah, so we're going to do inverse norm, or not inverse norm, excuse me. We're going to use normal CDF because we're looking for an area. And we could do minus infinity up to 129.71. I feel a little better doing 0 up to 129.71 personally, because you can't have negative lap times, right? Obviously, that just doesn't make any sense. So I want to go from 0. If you did negative infinity up to 129.71, it would give you exactly the same answer. Your calculator's not going to be able to tell the difference between those. So we just go here, normal CDF, 0 up to 129.71 with the standard deviation of 2.28. Wait, what? No, excuse me, I messed that up. 130, 129.71, I apologize. 8, there you go. About 55%, 55.06%. All right, what else did they ask? The fastest 3% of her laps are under some number. So they're giving us a probability or an area. So they want to know what the third percentile. I don't know why the 3 percentile. It's so weird, but let's see where they are. So this is 129.71. So third percentile somewhere over here. That's question mark, and this is 0.03 is this area. So I'm going to do inverse norm of 0.03 with a mean of 129.71 and a standard deviation of 2.28. Let's do it. Inverse norm 0.03, mean of 129.71, standard deviation of 2.28. Left side, paged away, 125.42. So this is a number of seconds, right? So it takes the 3% So 3% of all of her laps are faster than 125.42 seconds. So 125.42 is the third percentile. Last question, the middle 80% of her laps are between this and this many seconds. So the middle 80%, let's draw another picture because I think it would be helpful here. So the middle 80% looks like this, right? So here's this is 80% is in there. And the question that they're asking is like, what are these boundaries here? Well, the thing to notice is that if there's 80% in the middle, then there's 20% on the outside, and that 20% is split into two tens, right? So if there's 80% here, then there's 10% in there and 10% in here. And so this left question mark is the 10th percentile, and this right question mark is the 90th percentile, right? 10 and 80. So there's 90% of the area to the left of this, 10% of the area to the left of that. So if you're using left on your calculator, like I'm going to, we just do inverse norm of 10%, 0.7, right? And that gives me the 10th percentile. And then we do the same thing again to get the 90th percentile. Just change this to a 9, paste that in. And so it's between these two numbers, 126.79 and 132.63. Now, if you happen to be using the VMware version, this is where center actually comes in a little bit helpful. It saves you just a small amount of work here, right? We can just do the middle 80% by switching this, by doing this, right? That's what center does. So I've got 80% in the center, which is literally what they asked for, and it tells us these two numbers, right? So notice those are the two numbers that we got before. So you can save yourself a very small amount of work if you happen to have the electronic version of this calculator. Everybody has it if you happen to be using the electronic version of this calculator. Yeah, there you go. Feel free to use that if you want to. No big deal either way. All right, that was the last one from chapter 6. Now we are on to chapter 7. So let me go call that up. I should probably had this one queued up, but I didn't. So this is all about the central limit theorem. And I don't remember. Oh, we're starting with, I do remember these. So we're starting with this. So before we go any further, the key to using the central limit theorem correctly is knowing when to use it, right? The actual math or operations that you have to do are very, very small. You literally just divide the standard deviation of the population by the square root of the sample size to get the distribution of X bar. That's it. It's literally one division. That's all you have to do. That's not what makes this hard. What makes it hard is that you have to know when to do that and why. I guess you don't really have to know why. You have to know when to do that. And the time to do that is when you are asking about the average of a sample of several data values. So for instance, let's look at number 1 as our example here, or excuse me, number 1 through 6 is our example here, and I'll talk about that a little bit more. So let's read. Uni is a personnel manager in a large corporation. Each month, she must review 16 employees. From past experience, she has found that the reviews take her approximately 4 hours each, with a standard deviation of 1.2 hours. So 4 hours each is the average, right? So mu is 4. Sigma is 1.2. X is the random variable representing the time it takes to complete one review. And we're assuming X is normally distributed. Let X bar, and I don't know why their typesetting is so bad for this, but this is X bar. Like that bar that they've put kind of, 2/3 of the way up to the previous line and not all the way over the whole X. That's their bar for X bar. Sorry, I don't know why they don't fix their typesetting. There's got to be a better way to do it than that, but that's what it is. Let X bar, capital X bar, notice, be the random variable representing the mean time to complete the 16 reviews. So notice that capital X here is the distribution of the time it takes to do the reviews one at a time. This is the distribution that you get when you do 16 reviews, then average those times together, and then take that one number, that one average, and graph that, and then you do that for all of them, that's capital X bar. So that's a sampling distribution. So remember that term. We'll come back to that a lot. Assuming 16 reviews represent a random set of reviews. Okay. All right, so what's the mean standard deviation and sample size? Means 4, standard deviation is 1.2, sample size is 16. All right. These, so X has that distribution that we said earlier that's normally distributed, so N, with a mean of 4 hours and a standard deviation of 1.2 hours. That's what goes here. X bar, normally distributed. Central limit theorem still tells us it's normally distributed if we meet the two requirements, or excuse me, if we meet at least one of the two requirements, either population is normally distributed or sample size is large, which sample size here is not large. We want to be over 30 to count it as large. But the population is normally distributed, so we don't even need that. Anyway, it's normally distributed with a mean. So the mean's the same. That just you just bring it right down. So 4. And the standard deviation, you divide by the square root of the sample size. So the standard deviation of the population is 1.2. This is 1.2 over the square root of 16, which is 0.3. Right, square root of 16 is 4. 1.2 over 4 is 0.3. So these two guys are very similar distributions, right? They're centered the same. And then the only thing that changes is the standard deviation is smaller by a factor of the square root of the sample size. However, they're numerically similar, but they do not represent the same things. This distribution up here is a distribution of times of reviews. This is not. Each thing in this distribution here is an average of 16 times. It's not just one time, right? So there's no element in here that is just a single review. They're all combinations of 16 averaged together to get this to get what this distribution is. So you're not actually comparing like things here when you compare these two distributions. So don't think of these as the same. I know everything looks very similar, but the meaning here is quite different. So be really careful of that. That's the hard part about the central limit there. Okay. Find the probability that one review will take uni from 3.5 to 4.25 hours. Sketch the graph, labeling and scaling the horizontal axis, shade the region corresponding to the probability. Okay. So I'm glad they highlighted this, right? One review. So when we're doing the reviews one at a time, we are using the population, not the sampling distribution. So here we've got one of the things that's a little awkward here. I'm gonna ignore that. I'm just gonna make my own drawing. Let's make a new one. So this is N for 1.2. So 4 goes here. And they said 3.5 to 4.25, right? So 3.5 is over here. And yeah, I know this is I'm not being careful with the scaling, as always. 4.25. So if we want to find this area here, right, so that's the probability that one review takes between 3.5 and 4.25 hours, we use normal CDF. Normal CDF of 3.5 up to 4.25 with a mean of 4 and standard deviation of 1.2. Let's go do that. Normal CDF, that's 2 of 3.5 up to 4.25 with a standard deviation, or mean of 4 and a standard deviation of 1.2. So then 24.4%, 24.41, I guess, percent. So that's the area, or that's the probability that we're looking for there. Oh no, they just want you to write that, 3.5 to 4.25 equals 24.4%. Find the probability that the mean of a month's reviews. So now we're not talking about a single review. Now we're talking about the average of 16 of them, right? Because that's how many it does. Will be between 3.5 and 4.25. So that's very similar. Like the math is like what we're going to do operationally is almost exactly the same. But the meaning is different, right? So this is going to be n for 0.3. Still 4, and now we're going from here to here. This is still 3.5 to 4.25. This number is going to be much bigger because the standard deviation here is smaller, right? We have to go many more standard deviations to get from 4 to 3.5 now than we did over here. In fact, 4 times as many because the standard deviation is 4 times smaller, right? And so there's going to be a lot more area in here, although even though I've drawn them kind of the same, because like I said, I'm not trying to be super accurate. I'm just trying to get a nice visual aid. So we're going to do, now, like I said, operationally, we're basically doing the same thing, right? I'm looking for kind of a very similar area. So I'm just going to do normal CDF from 3.5 to 4.25 with a mean of 4 and a standard deviation of 0.3 instead of 1.2. Let's go here. So same thing, right? So in fact, if you want to cut down on the work a little bit, you could even do this, right? And just change this to 0.3, right? That's literally the only thing that changed here. Number is a lot bigger, about 75%, because we had to go so many more standard deviations to, because the standard deviation was so much smaller. And they say, you know, what causes the probabilities to be different between 3 and 4? And the answer is that those are different distributions. We're talking about different things, and one of them has a much larger standard deviation than the other one. So I'll let you go ahead and read my explanation in the text version if you want. It's over here, right? It's a paragraph long or something like that. It's this. So feel free to read that. I'm not going to go over it right now, but I hope you get the idea. But if you don't, read it and think about it. And the number 6, find the 95th percentile for the mean time to complete 1 month's reviews, right? So we're not using the population, now we're using the central limit theorem, and they want the mean time for 1 month's reviews, so that's going to be inverse norm of 0.95 with a mean of 4 and a standard deviation of 0.3 because we're talking about sampling distribution. So let's go find that real quick. Inverse norm of 0.9, mean of 4, standard deviation of not 1.2. It's the opposite of what I said. 0.3, left side. 4.38. No, 95th percentile. Sorry, I did 90th percentile. I apologize. I was going to say that doesn't seem like what I remember getting. There we go, 4.49. That's the thing I remember getting. All right, so there you go. 4.49 is the 95th percentile. Notice that this is a number of hours as well. It's a number of hours that has 95% of all possible averages less than it. So it's 95% likely that her average number of hours per review over a month will be less than 4.49 hours. Okay, back to the book here. Oh, I forgot what question we're on here. What number are we on? 63. Oh yeah, that's right. We jump all the way over there. So 63 is about taxes. That's not the right. It's this one. So according to the IRS, the average length of time for an individual to complete IRS Form 1040 is 10.53 hours. Now, if you've never had to file taxes before, this is your basic tax form. Like it's the one that everybody sends in. Sort of. If you just if all your income was like from a job that gives you a W-2 form, then you probably don't need this form. This is a more complicated form. You can probably do 1040 easy. So don't think you have to go for a 1040. In fact, you probably don't, right? Unless you have, your own company, like you sell t-shirts on whatever, some website. I'm not thinking of any of them right now, and collect income from that. You might have to do a 1040. But anyway, that's a bit off topic. The distribution is unknown. Let us assume that the standard deviation is 2 hours. I have no idea why we are assuming this. We'll just take them at their word. Now, to be fair, They're just trying to come up with a an original situation where you can do use the central limit theorem, right? So we'll take them at their word. 2 hours, fine. If you're actually doing research, don't just guess at the standard deviation, though. It's not a good policy. Suppose we sample 36 taxpayers. Now, this number 36 is pretty important because we are generally thinking of, so we want to use the central limit theorem here, right? We want to talk about the distribution of X bar, and we're not going to know that unless we know what the central limit, or unless we can use the central limit theorem to find it. So the central limit theorem has two requirements, of which we have to meet one. Doesn't matter which one. Either the underlying population is normally distributed, or the sample size is large, which is, for us, large means 30 or more. Here they specifically say that we don't know what the distribution is, right? The distribution is unknown. So we can't use the first of those. We have to hope that we took a big enough sample, which we did, right? So we randomly sampled 36 taxpayers. That's big enough for our purposes. So got to watch out for that, especially with unknown distributions. All right, so X is the population distribution, right? So it's the distribution of lengths of time that taxpayers take to fill out their 1040s. X bar is the average length of time 36 randomly selected taxpayers take to fill out their 1040s. So this is the distribution of a bunch of averages. This is the distribution of a bunch of people doing their tax returns one person at a time. This is groups of 36 people, the average time of a group of 36 people. X bar, it is normally distributed with a mean of the same mean, so 10.53, and a standard deviation that is 2 over the square root of our sample size, which is 36. 2 over 6 is 1/3. So this right here is like 0.33. Would I be surprised if if the 36 taxpayers finished their Form 1040s in an average of more than 12 hours? Yes, I would be very surprised. We can calculate the probability, but we don't actually really need to. Because the standard deviation here was 0.33, and this is 1.5-ish hours above the mean. So a standard deviation, so 1 hour above the mean would be 3 standard deviations away from the mean, which, if you remember the empirical rule, we would know that 0.3% of data is outside 3 standard deviations. So it would be like 0.15% for an average of 36 taxpayers to finish their 1040s in 11.5 hours, let alone 12, which is another like 1.5 standard deviations. So it's really, really unlikely that the average would be more than 12 hours for 36 taxpayers. Same question, but 1 taxpayer. So now we're using standard deviation of 2 hours. I wouldn't be that surprised here, because 2 hours is, so if it was 2 hours above the mean, that would be 12.53 hours. This isn't even that far. And so this is less than 1 standard deviation above the mean. So I wouldn't be particularly surprised. This is probably about 20% likely, something like that. Not the majority, but certainly it's going to happen plenty. But I'm sure you probably know somebody who takes more than 12 hours to do their taxes, right? Just if your parents have own their own business, or if you had income from multiple investments, or there's all kinds of things that would cause you to take a long time to do these. Anyway, that's a bit too much of an aside. So the other questions were 64, 65, and 68, if I remember correctly. All right, suppose that a category of world-class runners are known to run a marathon in an average of 145 minutes with standard deviation of 14 minutes. Consider 49 of the races. Let X bar be the average of the 49 races. That's not exactly right. We want to think of X bar, capital X bar, as the distribution of the average times from the 49 races. So like we take one person and one person that's in this class of world-class runners, and we take their times from those 49 races, and we average them together, right? And then we do that for everybody, and we should get and that's the distribution of X bar essentially. I think that's what they're getting at here. It's a little unclear. Again, I just want an excuse to practice central limit theorem. Not that concerned if the setup's a little wonky. X bar is approximately normally distributed because we have sample size over 30. Do we know they're normally distributed? We don't actually. So it's necessary that we have a sample size over 30 here. So normally distributed, and mean is the same mean, it's 145. Standard deviation is 14 over the square root of 49. The square root of 49 is 7. 14 over 7 is 2. So this is 145, 2. Find the probability that the runner, one of the category, anyway, will average between 142 and 146 minutes. So let's draw a picture. Okay. So we got, all right, so notice I'm only drawing the sampling distribution here, not the original population, because we actually don't know what the original population distribution is. All we know is that the sampling distribution is normal, the mean of 145, and a standard deviation of, I guess I'll write it all in, right? It's 14 over the square root of 49, which is, that's just 2. Sorry, I moved my window there. That's 2 here. So we had 145 here. And they said, what's the probability it's between 142 and 146? So 142 is over here somewhere, 142 is over here, and 146 is over there. And so we're going to do normal CDF, right? I want all this area in the middle. So we're going to do normal CDF from 142 to 146 with a mean of 145 and a standard deviation of 2. So let's pop over to the calculator to do that. Distributions, normal CDF, 142 to 146 with a mean of 145 and a standard deviation of 2. 62.47%. So there you go. That one. Find the 80th percentile for the average of these 49 marathons. We're just going to do inverse norm of 0.8 with the same distribution. So let's go do that. So inverse norm. That was not the thing I meant to do. Inverse norm of 0.8 with a mean of 145 and a standard deviation of 2. Left side. 146.68 is the 80th percentile. Notice that 80th percentile here is bad, right? You want to be lower percentile because lower times mean faster races, right? You want a lower time. So 80th percentile is like the bottom 20% basically of runners in this category at least. Right? If you're finishing a marathon in 145 minutes, you're doing pretty good. That's 2 hours 25 minutes, which is pretty fast. Find the median of the average running times. Well, normal distributions are symmetrical. Median is the same as the mean in symmetrical distributions. The mean here is 145, so the median is 145. This is another weirdo setup for this. The length of songs on a collector's iTunes album collection is uniformly distributed from 2 to 3.5 minutes. That seems unlikely to me. It's probably not the case that song times are uniformly distributed. They're probably normally distributed, although I don't actually know that. But they claim they're uniformly distributed from 2 to 3.5 minutes. Suppose we randomly pick 5 albums from the collection. There's a total of 43 songs on the 5 albums. Okay. This is confusingly worded in the following way. They're talking about 5 albums from the album collection, but that's not the information they give us about the mean, right? The mean they tell us is, so that the distribution is uniform of the length of the songs, not the albums. So the 43 songs are from this distribution, uniform from 2 to 3.5 minutes, which, by the way, the person who wrote this song does not appear to know how long songs are. 2 minutes is really short, and 3.5 minutes is pretty medium. The maximum value of the songs in this collection should probably be higher than this, but whatever, we're just going to run with this, right? So this is the distribution of songs, of the song length, not album length. And we got 43 songs. So we're ignoring the fact that they're from 5 albums. This is an albums collection, right? We're thinking of this as songs from this distribution. We have 43 of them. What's the distribution of the mean lengths of those 43 songs, right? That's really what we're asking about here. So in words, X is the length of the songs, the distribution of song length in this collector's album collection. And X is not normally distributed, it is uniformly distributed, right? So that's really important here. Let's go get a whiteboard going, right? So the population is uniformly distributed from 2 to 3.5, right? So the length is this. 1, 2, 3, 4. This is the population. The sampling distribution, because we have a large enough sample size of 43, right, bigger than 30, the sampling distribution is normally distributed with a mean of the same mean and a standard deviation that is the square root of 43 times smaller. So what we need to do is we need to find the mean and standard deviation of this guy, right, which they didn't give us, but they did tell us that it's uniform and what the edges are, 2 and 3.5. So if you remember, we can calculate them, right? So I'll let you go look it up, but the formula for the mean is 2 plus 3.5 over 2, right? It's in the middle here, which is 2.75, right? Yeah, 2.75. And the standard deviation is b minus a over the square root of 12. Right, this guy is u to 3.5, where this is a and that's b. When I say a and b, that's what I'm referring to. So this is 3.5 minus 2 over the square root of 12. And again, just flip back to your chapter 4 notes, the continuous, or I guess it's chapter 5, continuous random variables notes for these formulas if you don't remember them. And this, I don't remember what that number comes out to be, but of course I already found it when I did the homework, the text of the homework. Where is this? 65? Yeah, 65. Oh, I should probably switch over here. That one. Standard deviation is this guy for the sampling distribution. Oh, excuse me, I never found it here. Let's go find this. Let's go find the standard deviation for population. Standard deviation of the population is 3.5 here. I know it's 1.5, but 3.5 minus 1 minus 2 divided by the square root of 12, and that's always 12. So this 0.433 is the standard deviation of the population. This guy over here, the sampling distribution, is not that, right? So this is the mean is the same, 2.75, but the standard deviation is going to be 0.433, so it's sigma, over the square root of n, which n is 43 here. And this comes out to be 0.066 or thereabouts, I believe. Let's make sure I've done that correctly. So it's 0.43. Oh, I guess I can just do this divided by the square root of 43. Yeah, 0.066 is the standard deviation of the sampling distribution, or the standard error. I should just use the terms right away. So this is the standard error. 0.066. Right, but it's still centered at 2.75. So whenever we're asking about the mean length of 43 songs, we're going to be using this distribution here. So let's go see what they're asking us. I don't remember. X is the distribution of lengths of songs in this person's collection, and it is uniform. So U 2, 3.5, not N. X bar is the average of the lengths of 43 songs from this collection. It is normal, so this is an N with a mean of 2.75 and a standard deviation of 0.066. Find the first quartile for the average song length. So first quartile is 25th percentile, so we're going to do inverse norm of 0.25. Norm 0.25, mean of 2.75, and a standard deviation. This is for X bar, yeah, of 0.066. 2.705. And then the next question is to find the IQR. They didn't actually ask for the IQR. They wanted the bounds for the middle 50%. So they want the 75th percentile, which is literally the same calculation, but with a 75% instead of 25%, right there. So there's your bounds, 2.705 to 2.795. All right, one last question. Percent of fat calories that a person consumes is normally distributed with a mean of 36 and a standard deviation of 10. We did this one earlier, or we used this distribution earlier. Suppose 16 individuals are randomly chosen. Let X be the average percent of fat calories for those 16 individuals. X bar is approximately normally distributed with a mean of 36 and a standard deviation of 10 divided by the square root of 16. So square root of 16 is 4, 10 over 4 is 2.5. So this number is 2.5. For the group of 16, find the probability that the average percent of fat calories consumed is more than 5. I don't know why this is a 5. It's a weird choice on the author's part. I think it's probably a typo. I didn't notice that when I first assigned this. I'm sorry. It's going to be basically 100%, but let's go ahead and graph it anyway, right? Got to get good habits going here. So we have distribution. This is a normal distribution with a mean of 36 and a standard deviation of 10 over 4, which is 2.5. So 36 goes here. They said, what's the probability that their percent of fat, percent of calories from fat is more than 5? So 5's over here somewhere, right? It's actually much further away than that. It's basically 1. You would do normal CDF of 5 to infinity with a mean of 36 and a standard deviation of 2.5. I may as well do that. Since we are here, right? We're here to practice. So normal CDF, standard lower bound's 5, upper bound is a lot, mean is 36, standard deviation is 2.5. Paste. Lo and behold, it's 1. Now, not actually 1, right? It's just some number that is like 0.999999999, and then probably some more 9s. That your calculator is rounding up to 1 because to 10 decimal places it's indistinguishable from 1. So I assume that was a typo. It was probably left over from a previous version of the problem where they were asking about something else, and 5 was a relevant number, is my guess. But anyway, there you go. Find the first quartile for the average percent of fat calories. So 25th percentile, inverse norm of 25%. Let's do it. I should probably switch back to the calculator here. So inverse norm, 25%, mean of 36, standard deviation of 2.5, left side, 34.31 is the first quartile, or the 25th percentile, or the cutoff for that. All right, and that is it for this lengthy homework. Normal distributions are really important, so I want to make sure we're good with them, that you guys know how to use inverse norm and normal CDF. If you're having trouble, don't hesitate to come ask me questions and review the old videos. So I'm going to go ahead and stop the video here, and I'll see you guys in the next one.